Hello everyone. In today's session, we're going to be talking about related rates. Related rates have a connection with chain rule. Let's see how they are related to chain rules. As usual, we talk about the topics we have covered and what we are going to be covering in this session. So in our previous lectures, we have talked about derivatives of function using different rules like constant rule, power rule, sum and difference rule, product rule, quotient rule, chain rule, and implicit differentiation. Also, we have found derivatives of trigonometric and higher order functions. In this lecture, we're going to be focusing on related rates and use them to solve real-life problems. So let's begin with finding related rates. Now, keep in mind that we have talked about chain rules and how they can be used to find a differential of a function implicitly. Remember, when we have implicit functions, we do implicit differentiation. And in order to do implicit differentiation, chain rule was a major factor. So in this session, we're going to look at another important use of chain rule. Here, this use of chain rule helps us to find the rates of change of two or more related variables which are changing with respect to time. So let's start with an example. So suppose a water is filled in a conical tank. Now, if we cut the base of this conical tank, the water is going to start draining out. Now, initially, before the cut was made, it was filled to the brim. The water was filled to the brim in this upside down conical tank. Notice, as the water is filled over here, so this is my conical tank before the cut is made. So there's some water over here. Now, as there's some water, so the water will take the shape of this conical tank, and you notice that the volume, the radius, and the height of this water are all functions of time. Now, what we do is we make a little cut over here. So we make the cut here, and what happens is the water starts to drip. So when the water starts to drip, what is going to happen? This water which was in the conical tank is going to go down. And as a result, after some time, notice this is where the water is. So this is the water now here. The level has gone down. So this is now where the water is. And now the height has decreased, the radius has decreased, and the volume has decreased now because this is where the water is. Similarly, after further more time, what you notice is the volume goes further down. More of the water has come out of this conical tank. So what we're noticing is that all these variables, the volume, the radius, and the height, they change as time changes. So we notice a rate of change of here 3 variables with respect to time. And not only that, all these variables are related by an equation. Because this water is filled in a conical tank, so the volume would be related to the of the conical tank. So here the volume is given by pi 3 r square h. Now we can actually differentiate this function, this relationship, or the function we can say of volume with respect to time, to obtain the related rate equation. Now remember what we were given. We're given V as pi 3 r square h. Now all of that we have seen that in that picture, as time goes by, the volume decreases, the radius decreases, and the height decreases. That means there's a rate of change of one variable with respect to time. Rather, there are three variables which are changing. So in order to differentiate this, because remember differentiation is also looked as a rate of change. So the differential of this volume with respect to time is basically the differential of this equation on the right hand side of the equal sign. So basically we are now doing implicit differentiation. So when you take the differential of v with respect to time, now here pi third on the right hand side, you can take that out. It's a constant. And then what we are going to be left? We have pi thirds differential with respect to time of r square h. Now remember, r in t and h in t are different. Now before we go and apply differential, you have to see what kind of a relationship we have here. So we are having two functions which are multiplied to each other. So in order to do the differential, we have to first apply over here, we have to apply the product rule. Remember that, guys. So when we apply the product rule, my r is the first function, h is the second. So, well, okay, I have done it over here, written it opposite, it doesn't matter. So what I'm doing is I'm taking the differential of the second times the first function plus the second function times the differential. So I can write this as pi thirds r square differential of the second function plus h differential of the r square. So this differential of r square, remember r and t are different in h, so what are we going to have? So this will, you take the normal differential, you're doing the chain rule. Remember the chain rule, u to the power n. So what is dy by dt? It is n u n minus 1 times du over dt. That's what we're doing, guys, here. So this one, when you take the differential of r squared, becomes dr over dt times 2r. And then just write in a much more nicer form, basically taking away the brackets. So what we get is dv over dt is pi third times, inside the square brackets, r squared times dh over dt plus 2rh dr over dt. So what we are noticing here? We notice that the rate of change of the volume, v, is related to the rates of change of both the height and the radius r. Okay, that's how we apply the chain rule, and we can see how it is used in real life problems through related rates. Let's look at another example. It says the variables x and y are both differentiable functions of t. And there is a relationship between x and y, which is given by y equals x squared plus 3. We are asked to find dy by dt when x is 1, given that dx over dt is 2 when x is 1. So we want to find dy by dt. Okay? So we want to find dy by dt. That means we're going to find the differential of x squared plus 3. So the differential is with respect to t. Now remember, y and t and x and t, they're not the same variable. So what does that mean? We got to apply the chain rule. Okay, so when you apply the differential on x squared plus 3, so differential of a constant is 0. But differential of x squared is what? 2x times dx over dt. So the question says find dy by dt when x is 1, given that dx over dt is 2. We have to be given x and dx over dt to find dy by dt. So what we need to do is just, substitute the values for x and dx over dt. Our final answer for dy by dt is 4. Now here are certain guidelines to solve related rate problems. The first and foremost is you need to read the problem very carefully and then start to look at what the problem is telling us. We look at what given quantities are there, what is the quantity to be determined. If we can make a sketch, that's awesome. If not, that's fine. And we also label all these quantities. We give them some variable names. And then we say, is there any relationship or equation between these variables? If it is, we write that equation, which involves the variables whose rate of change either are given or are to be determined. And then we apply the chain rule, do implicit differentiation on both sides of the equation with respect to time t. Very important, guys, it is the time, which is a very important factor. Now, after completing the above step, we substitute into the resulting equation all known values for the variables and their rate of change, and then solve for the required rate of change. Okay, now let's go ahead and do an example. So we're going to talk about ripples in a pond. A pebble is dropped into a calm pond. And as a result, there are definitely going to be ripples in the form of concentric circles, which is shown over here in this picture. Notice the radius of the outer ripple will increase. So it's going to definitely increase. But according to our problem, the radius of the outer ripple is increasing at a constant rate of 1 foot per second. So this wording, increasing at a constant rate, this basically is showing us that there is a differential. Okay, there's a differential happening. There's a differentiation here. Now, the question says, when the radius is 4 feet, at what rate is the total area of the disturbed water changing? The rate of change. Remember, the rate of change is nothing but dy over dt or dx over dt, depending upon what variables we're using. Okay, so now we have read this problem, and something is showing us that when a pebble is drawn, we are getting concentric circles. Okay, that's the key, is that's where some relationships of a circle will be starting coming up. Then we're saying that the radius, that means one of the variables is a radius, and the question says total area. So that means there we are looking at the radius, these are the variables we can look at, and the area. Because we're looking at concentric circles, they are increasing. That means we're looking at the area of the circle. So we all know what is the formula. So we can say let my area be A, let my radius be R, and we know the relationship of area of a circle, because it says it is forming concentric circles, is pi r square. So now we have found the variables. We have also found the relationship between the variables. And now we're also looking, when we read the second line, it says the radius is increasing at a constant rate of 1 foot per second. So this simply says that dr over dt is 1 foot per second. Okay, the next line, the last sentence says, when the radius is 4 feet, at what rate is the area changing? That means it is asking, what is dA over dt when our radius is 4? Okay, now we're going to write that down. It's nicely written in the next slide, guys. So the variables, as I wrote in the previous slide, was r and a. They're related by this equation. So r, remember, is the radius, and a is the area. Now the rate of change of the radius r is dr by dt equals 1 foot per second, and we're asked to find dA over dt. So now remember, we have to do the implicit differentiation on this equation which shows the relationship between the area and the radius. So we write dA over dt is dt of pi r square. Now pi is a constant, so we take the pi out, differential of r square. Now r, remember, is a variable representing a quantity here, it's a radius. So r and t are different, that means chain rule. So we write this as 2r. So what do you get? Which is pi times 2r dr by dt. And we have written in a much more nicer form here on the note. So it's 2 pi r dr over dt. My mistake. Okay, so now we have got this one, and now we have to find that if my radius is 4 and the rate of change is given to be 1 foot per second, so what is the rate of change of the area? It is 8 pi. Just substitute the values. So what we notice, when the radius is 4 feet, the area is changing at a rate of 8 pi square feet per second. Be very, very, very of the variables and their units. Area will have, area means you'll have either length or a breadth. So here in the circle, so it's going to be having 2 dimensions here. Okay, so there are some, next slide talks about some mathematical models and rate of change in that. So let's look at some verbal statements and how do we write a mathematical model for it. So if a velocity of a car after traveling for 1 hour is 50 miles per hour. So now remember the velocity, we have done these problems. Velocity is the rate of change of distance with respect to time. So if my s or here is x, so x is the distance traveled, or I wrote as s. So dx over dt is 50 miles per hour. Now let's look at, so here it is just x rate of change of the distance. Now suppose if a water is being pumped into a swimming pool at a rate of 10 cubic meters per. Now remember, water is being pumped cubic. That means we are having volume. So water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. That means we're looking at the volume of the water in the pool. And when there is a change, then dV over dt is 10 meter cube per hour. Cubic meters, or we write meter cube. Now if you're looking at some physics kind of a problem where you have a gear is revolving at a rate of 25 revolutions per minute. Now remember, 1 revolution is 2 pi radians. So theta is the angle of revolution. So d theta over dt is 25 times 2 pi radians per minute. If you're looking at population, so if a population of bacteria is increasing, that means we're looking at number of bacteria here. So if x is the number in the population, according to this problem, dx over dt is 2000 bacteria per hour. So this just gives an idea when you're looking at a problem. Oh, we are looking at volume, we are looking at velocity, population, all those things. Okay, one more example. It's a spherical balloon is inflated with the gas at the rate of 800 cubic centimeters per minute. The question is, how fast is the radius of the balloon increasing at the instant the radius is 30 centimeters or 60 centimeters? So let's look at what is given and what are we being, asked. So the first sentence gives us a big picture. It's a spherical balloon. So basically we know the object figure. It's a geometric object, which is a sphere. And it is basically a balloon. When it's filled with air, it becomes a spherical in shape. It is inflated with gas at the rate of 800 cubic centimeters per minute. This cubic is a giveaway. We are looking at volume. Okay. At the rate of, that means we're looking at dV over dt is 800. It is cubic centimeters, so it's centimeters per cube per minute. Okay, now that gives us an idea that we are looking at this volume of a sphere. Now the next line says, how fast is the radius increasing? Because if you fill up the gas in the a balloon, then slowly it will increase in shape, the radius will increase, the volume would increase. Okay, so the question is, how fast is the radius increasing? In other words, if my radius is, say, represented by r, it is dr over dt. Now the variables r and v, because it's a spherical balloon, are related by this relationship v equals 4 over 3 pi r cubed. Now the rate of change of the volume is dV over dt is 800 cubic centimeters per minute. And we're asked to find dr over dt when the radius is at 2 different units here, 30 centimeters or 60 centimeters. So what's the normal thing we do? Because we have to find the rate of change of r. So we're going to first of all differentiate this equation. And when we do the differentiation, what do we get? We get dv over dt is d dt over 4 over 3 pi r cubed. Okay, now 4/3 is a constant, pi is a constant. So we take the 4/3 pi out and we take the differential of r cubed. R and t are different variables, so you do the normal differential, that is 3r squared times dr over dt. Now clearly 3 and 3 are they can cancel out each other. So what do we get? Because 800 is already given to us. 800 equals 4 pi r squared dr over dt. Now the question is, how fast is the rate of increase of radius? That means you're solving for dr over dt and put everything else on the other side of the equal sign. So when the radius is 30 centimeters, so what is the rate of change of the radius? Is replace the r by 30 and you get 2 over 9 pi centimeters per minute. It's very important, guys, that you write down the correct units. Okay, when the radius is 60 centimeters, the radius is changing at the rate of 800 over 4 pi times 60 square, which is equal to 1 over 18 pi centimeters per minute. It's okay with me, guys. I'm not looking at decimal answers. This one is more than enough. Okay, so we have done some examples here for related rates. It's time for us to practice. So here are some practice problems. They're very similar to the things I have done earlier. Thank you.